So the outline of this presentation, so again, like it's a framework to estimate IBR control parameters featuring time and frequency domain data. So that's a rough outline. And a little bit about me. So my name is Kaio. I'm originally from Brazil, so I'm also doing my PhD in electrical engineering at DTU in Denmark. It's an industrial PhD, so it's a collaboration between Typhoon HIL and DTU within the InnoCyPES project. So let's start very straight, like what is the main motivation, and I try to be very concise here, like about what's the motivation of this. So, and I come with this sentence that all models are simply an attempt at emulating real-world systems inherently constrained by their specific domains of applicability and accuracy. So we as engineers, we love models, right? And for example, we have, of course, like very complex models, and we have simple. Right. This, for example, is to explain an idea. I decided to use this very simple model. Right. Is and I have this question: and what makes this equation accurate in representing a real-world linear relationship? Right. So, for example, if you have data, so we get data, so we are through these measurements, through this data, we have a notion of maybe a relationship of some phenomena that happens in the real world, right? And then by looking at this data and you have some variables, you can say, well, so this can be represented as a linear model. There are some noises there, but I can represent it as a linear model. So that equation that we have above, this representation, can, in these circumstances, right, nicely represent that phenomena. But like this is the model structure that we have, but there is also these parameters, right? So we have, for example, the M and we have the B in that equation above, right? So if we just like blindly place this line there and believe that it can represent that physics, that real world phenomena, we might be wrong, right? So it needs some calibration. So if so it's important to have this good model, but not just a good model. You need to have a good calibration of these models. Otherwise, this line can be placed completely wrong and could not represent the relationship that we have in this from these measurements. So here we have some other examples. Right now, imagine this other case in which we have those data here, this approximately linear data. So if we try to represent via this linear model, still there are some points that might be accurate, but some that may be not that good to represent that specific phenomena, right? And there are some cases in which we don't have a linear data, in which if we try to use this linear model, we won't be able to do that. But here I even, like this is interesting because that linear data, we have here a region in which we could be useful to represent it via this model that we represented. And in engineering, do it all the time, right? So we usually, sometimes we have this small signal idea in which around a certain region, maybe that model that we have limited limitations, but can be somehow useful to represent a specific physics, a specific phenomenon, right? So it's important to understand here. So I'm coming with this simple example, but in IBRs, which is inverter-based resources, right? So, for example, PV, right? That's interface with a real converter. All these kind of things, we try to represent it as models, but they are highly nonlinear, right? So again, it's important for us to have a good representation of these models. It's first important for us to have a good model, first of all, and afterwards there is this concern on how to calibrate this model such as it can be used. Otherwise, it doesn't matter if you have a pretty good model, but if it's not calibrated, it's not representing what you want, right? And at the same time, it doesn't matter, you can do whatever calibration you want to do, but if the model is pretty wrong, like it doesn't represent the physics, you also be unable sometimes to represent it for the full range, but maybe for some specific range you can do it if it's well calibrated, right? So these are the main takeaways, right? So in real-world applications, accurate calibration of parameters is what makes the difference between a model that's useful and that's not. And without proper calibration, even the most sophisticated model can fail to give us reliable insights. And although calibration can help get a better approximation of a system behavior, model structures might have limitations that do not allow them to represent a system accurately enough for desired system states. So these concepts are important before we start, right? So here, the idea of this, the topic here, right? So it's a framework to estimate IBR control parameters featuring time and frequency domain data. So there are many ways of doing that. Here we are tackling it in this way. And the way that we are doing, that we are proposing here in this framework is related with the limitations that we have right now with these IBR control parameters. It's because it's related to IBRs, right? That's and you understand. I will explain it a little bit better. And we are proposing here using time and frequency domain data. So there are other authors that might propose a different approach. But why control parameters of IBRs, right? This is an interesting question, right? So, of course, like we have this higher penetration of IBRs over time. So they're becoming more and more important because we are um, we have this demand, right? We have this transition that we want to do in the energy sector, and it involves like using more and more wind, PV, and so on. So we have these inverter-based resources interfacing with the grid and increasing and increasing. So it brings some concerns, right? So how to model the IBR behavior then? So we are connecting it, how we can model it, how we can predict the behavior of them. And the controls are critical because they affect the behavior of the system, right? So of the system, but they are usually black box. So this is a main issue when it comes to IBR controls. So that's why also we are presenting this framework, because differently from what we had in the past with the synchronous machine, in which there are many softwares that could be used to validate and help calibrate the parameters of some generic models that we had for the synchronous generators. Now we don't have it that clear, right? So because those models, they were more like white box, we knew what to expect. But with IBR controls, most OEM models are, in other words, like the manufacturer, they don't provide it because it's proprietary information for them. So we need to be a little bit more like some of the methods that we use for the synchronous generator, we cannot just extend for the IBR. Now we have a different challenge. And the main thing here is because of they are black boxed. So they don't, you have like different ways that you can model the control. Like it's, and we have the demand, we have this demand of models that are a bit more generic. And I will talk a little bit more about this. So it's like a deck, right, of cards that you have. So you have different types of tools, right? Different types of cards that you can use and models, strategies that you can use to represent some specific behavior that you see in the real world. And there is no one model fits all solution. So you need to be wise, depending on the application that you have, depending on the problem that you are plan to study. You take one of these cards and use it, right? So you have, for example, OEM models. They are very important also for certain periods during the certain studies. But we also have, for example, neural network based. Now people are talking about it, but they are still a bit iffy, so not very used in the practical domain. But it's people are researching it. There are these generic models, some aggregate models, ways that they can use to represent, like especially for the bulky power system, bigger systems, right? In which you have many different units of IBR. So how to put all of this together to conduct a study. So it demands a lot of computational power in a way. So while there are different possibilities, the choice depends on the use case, of course, right? So for example, how to calibrate and validate the generic or aggregate, because the OEM, it's a task that belongs mostly for the manufacturer. They run hundreds, thousands of tests. They try to do their validation and calibration themselves. Right? When it comes to the generic, right, model, maybe then we are not talking about the OEM, but someone who, let's say, a TSO who wants to conduct some studies themselves, and they have like the bulky power system, so it's not feasible for them sometimes just taking all the OEM models and putting them together, or if they want to do some planning studies in which they don't even know which manufacturer they use and that they will connect. So, and then a generic model can be very interesting, or in some cases they aggregate. So again, so all these models, they have some applicability. So they might be very useful for certain cases. So the ways that we can calibrate them usually involves using a reference. Right. So that synchronous generator, that the way that I told before was like, for example, they were many based on Kalman filters, but then you would need to know a little bit more about the state space models, things like that. But when you have like this black box model, and then the things become a little bit more complicated. But all of them, in a way, they involve like using some reference data. A reference data of some, in which you can get this reference data from a higher fidelity model, or the real system, some real measurements. So you usually get it from something that you can trust. And so you validate or you calibrate against something. So you want to calibrate something to behave more closely to some reference in the end, right? And so that's why I put all these arrows pointing. So sometimes it might be measurement, sometimes it might be a Hill setup. What's a Hill setup that I'm saying here? It's a hardware in the loop setup. And hardware in the loop involves like using the real controller, in this case, in the simulation loop. So this is also a pretty good high fidelity way of, using because you are using the real hardware. So it's also can be pretty good. The OEM model, sometimes the OEM model, they even have the real source code of the controller running as a software in the loop in some cases. Yeah, so, but that's the idea. So you use a higher fidelity model. So just again, to understand, so here our focus is on generic models. So that framework, although it can be extended to all these other cases, in this example that we are using, this specific use case that we are testing this framework, we are focusing on generic models. And here we want to talk a little bit more about the importance of these generic models. So since the early 2000s, right, so the widespread integration of wind energy into global utility grids has created a demand for, we have this keyword, right? Standardized, public, flexible, and well-documented models for interconnection-wide stability studies. So given this demand, so there were several attempts in the early 2000s to come up with some standardized, public, flexible, and well-documented model. And it started, for example, there were many initiatives. One of them was the SIGRE working group, this C4.601. So they've tried, but they failed to bring a detailed and public model because of IP concerns. So actually, very few, like when they gather together, like you have these working groups with a lot of stakeholders, a lot of people participating. And some of them, they were not willing to really share data when it came to, okay, let's create a generic model. And when they come to see if that generic model was relevant to represent a range of manufacturer models there, if that could be really called generic, let's say. And then they were not willing to really share much data and kind of things. So they failed a little bit in this sense. And then in 2004, this WECC, so it is in the US, in the institution in the US, that's they started this task force, which is the Wind Generation Modeling Task Force, under the Modeling and Validation Working Group. And then they released the first generation of generic and publicly available wind turbine generator models at that time, 2004. But then in 2010, they released the first generation. 2010, there were complaints about the biased model. So they said, this is not really generic, because it looks like like it can represent kind of well like a specific manufacturer, But indeed, like not many manufacturers were willing to share data, but one did, and they built like most based on that one that who shared. And so in the end, that's why that was biased, of course, right? But then in 2010, NERC, it's another American institution, issued a special report highlighting the disparate need for public and standard generic models for variable generation technologies. And then they broadened it. So it was like a claim, right, that we need it desperately. And they renamed in the end this task force for energy. They started calling it the Energy Modeling Task Force. And then in 2014, they released the second generation wind turbine generator, the PV, and also battery energy storage system. So they broadened these generic models. And I suggest if you are interested to look more into these models, generic models. So why it's interesting here, so the use case that we used, we based our generic models on the generic models that they provided here. That's why I'm also talking about them. So you can access, see, it's still an ongoing effort. They've been study like still working on these generic models, and they present it as modules. So you can have modules for these generic models. Of course, there are limitations of the generic models, but there are a lot of documents that explain the limitations, that explain what was the idea of this generic model, what was the purpose of these generic models. So you can see more about them there. So let's jump into the framework, right? So this is the framework that we are presenting right now. So the first thing is that, okay, I have a model, a generic model, let's say, and let's define the key parameters to estimate. So what I want to calibrate in these models. And then you can design the test cases. And here we are proposing to use time domain data and also frequency domain cases, or time domain cases, or yeah, so time domain data, frequency domain data to help you calibrate these parameters. And then you can define the cost function calculation approach and so on. So it involves like the error metrics that you use and how you calculate the cost. So I will explain a little bit more later. So this is the conceptual phase of the framework, and then it communicates with this, right? So you can see the conceptual phase, and there is this optimization strategy tuning phase, and then in which the idea is to answer these questions: what tests are more suitable for estimating certain control parameters? Because there we are proposing using frequency domain data and time domain data, right? But there are different, ways in which you can collect it. So it's important that based on the parameters that you chose, you want to calibrate. So you need to see if there is sensitivity, right? If the tests, the data that you have, they are influenced by those parameters, right? This is important in this case. So it's like, okay, I want to see if by changing these parameters, can I need that response, that specific test case that I got, is it influenced by that parameter? Because otherwise, like you won't be able to really calibrate the parameter if the data that you are using is not related to that specific parameter, right? But then via this sensitivity analysis, you can also use it to group better the parameters. So if you have like a bunch of parameters, you select some test cases, you do sensitivity analysis here, and then you can group these parameters better and reduce the search space when doing the estimation and assessment phase. So this is a, iterative. That's why I put it like these two arrows here, because this conceptual phase, sometimes when you see that in the sensitivity analysis that you need to change some things in the conceptual phase, and then you can go back and do some changes. And here we use in the estimation and assessment phase, and then you perform the parameter estimation routine, and then you can extend to some test cases to validate the model against some other references, some tests that were not used through the calibration process, during the calibration process, to see how it can be generalized. And here we used a heuristic method to do that, because it's a black box system again, right? So that's the main reason why we decided to approach this way. And there have been other studies that opted for the same kind of approach, like using heuristic methods. So there are different ways in which you can do that. All right. Here we selected this PSO, which is particle swarm optimization, but we are not very interested in the method itself. We are seeing if this can be used, if this framework is relevant. And there are different other approaches like Bayesian optimization. There are this African voucher also optimization. So there are plenty of them. So maybe it's a matter of, after this framework is well defined, to expand these studies and then maybe compare the methods. But here the idea is really just to have a proof of concept to see if this kind of approach is useful and helpful for this goal, which is calibrating the parameters. So this is an example of another author who published a similar framework in a way, but they use PMU data. So here they use measurement data. So because they use this measurement data, you see that it's somehow similar to the one that I showed before. But our goal when we presented that framework was more to use simulated data, because we, as Typhoon HIL, so we are not OEMs. So some of our customers, they are interested in better calibrating their models. And what we can provide are more like generic models. So this is relevant for our customers, for example, in Typhoon HIL. And we have hardware-in-the-loop setups, so we can get some data from these HIL setups in which the controller is connected with the simulation loop to get that high fidelity reference and so on. But here in this framework that Bisu was presented, she actually used the PMU data, and then there were some differences like event detection, because she's getting data from the measurements, right? And is the focus, because PMU is the focus here, so there are some considerations that needs to be done. So this event detection, data preprocessing, disturbance recordings, and she also used some, if you have some events that happened after the calibration process, that's why there is this part over here, like down, right? That she's also, okay, if you have some new events, maybe you can recalibrate the model and so on. So that's also why she put it this part here, right? But she's using some sanity checks. She has this kind of approach that differs from our approach, that we have this idea. And this impacted the way that she chose the cost function. So in our case, we use the cost function that is an Euclidean distance, because we have, since we are dealing with, especially with simulation data, we are not constrained. We have control over the sampling. We don't have noise. We don't have all these issues that she has. So in her cases, she used a cost function calculation that considers, so she does some pre-processing, and she considers the area under the curve, and she wants to minimize this area between the reference data and the data that she's getting from her model there that she wants to calibrate. So this calibration process in the end, it's a very iterative process, especially in heuristic approach, right? You do a lot of testing. You do a lot of testing with different parameters, and then you test. That's the way that you do in the end. So this kind of cost function is calculated many times. So that's why that's the idea about the particle swarm optimization, for example, right? So it's like the idea of particle swarm optimization is like birds flock together. So you have these particles, you have a bunch of them, and each of these particles, they try a different set of parameters, let's say, and they get a result. They have a cost function associated for each particle there in that specific iteration. And they share information among each others in a way, right? That's the example here in this side of how a particle swarm optimization works. So you see that there is a swarm that's navigating through the solution space in a way, and they via this shareable information, they started getting closer and closer to the optimal solution, which is in the middle in this case, in this example. So in the framework that we use, these optimizations, like we run a bunch of simulations. Also, we have some reference data that doesn't change. This reference is always the same. But then we are moving this particle across the solution space, and then we're trying to find what would be the best set of parameters for that. Right. That's the idea. And so we change the particle position, and there is this velocity that's calculated using some hyperparameters that they call this cognitive parameter, the social parameter, inertia parameter. So we'll talk a little bit more about them. So if you want to fine tune this particle swarm optimization, for example, you can tune the cognitive learning rate, social learning rate, inertia weight. So there are different methods that you can use to tune hyperparameters, but they usually take a long time in a way. So if you just blindly try to calibrate them, it's important to have an idea of what the role of each of these hyperparameters before just diving into it, right? So for example, the cognitive learning, so when you increase it, there is more exploration based on the swarm experience, increasing the chance of finding a global optima, but slowing down the convergence. If you decrease it, and then you have the opposite effect in a way, right? The social learning, you increase this swarm knowledge sharing, like promoting exploitation towards the best found solution at that point, potentially neglecting other promising regions, and this inertia in which you give momentum to the particle, allowing them to explore further based on their previous direction, potentially missing some close optima also. So you need to find some common ground here in which you can balance well all these hyperparameters together. So how was the framework implemented? So in this use case, in the framework, we use the Typhoon HIL device. So we have, for example, here, this fourth generation devices. So again, Typhoon HIL, and then now I will explain a little bit more what Typhoon HIL is, right? So Typhoon HIL is this hardware in the loop simulation manufacturer. So they sell devices that accompany a toolchain, a software toolchain in which you can use to program the real-time simulator. And like there are different tools in this toolchain you can use to perform a bunch of tests, automated tests, and so on. So it was founded in 2008, and right now it has a bit more than 100 employees already. So this is the Typhoon HIL Control Center. And here you can see all the tools that we have there. So we have, for example, the schematic editor, we have the HIL SCADA, and we have the Typhoon Test ID. So if the schematic editor is where you put your model there, so you can create your model. The HIL SCADA, after the model is already created, you can use the HIL SCADA to monitor the variables, perform some actions, influence the simulation. And here you have this Typhoon Test ID. And there are some other additional tools that can be helpful too. I'm not going to go in details of all of them, but just to show like briefly what I'm talking about. And in my case, like in this framework, we used this integrated tool, this Typhoon Test ID, with a tool integrated with the Typhoon HIL API library, and we use to write, run, and manage Python tests. So this is nice because since it's a Python-based script, right? It's a library that we have. You can use Python to also automate tests. So that's how we did. So it's nice because you can already use the whole universe of Python libraries that we have out there, and you can also, let's say, like embed like all these things. You take the leverage all these Typhoon libraries that you have out there, and then use and here also conduct some, like capturing data from this HIL setup simulation, so on, perform some actions and this kind of things. So it's pretty nice and convenient. So in this case, we use this, for example, we use this library, which is PySwarms, that's written like that, is used for implementing the PSO algorithm in this framework. So if you want to know more about Typhoon HIL, we have free courses and free materials, and also you can download the software and get a free version, like I would say a license to use it and use it as a virtual HIL. So of course you are not gonna get the real-time device, but this real-time device, it can also run not in real time in this case, but as an offline simulator, but it can run in what we call virtual hill. And there you can understand better what's the idea behind this hardware in the loop simulation, right? What is this concept? But it has been used more and more over time, like as it has been proven to be very useful for engineers in many domains, in many domains. So there are plenty of free courses there. There is even this Hill Expert 2.0 in which you can take the courses and receive certificates, real certificates about it. And then again, so if you take this course, the Hill Expert there, you can download the software and have a free license to work with Virtual Hill in Typhoon Hill. So this is the website, Hill Academy. So as I said, so in this use case, we decided to calibrate a generic model of a grid following inverter, right? A grid following or an inverter working using this, let's say, control strategy, which is grid following. Inverters control, right, may be broadly classified into these two. Now people are trying to invent more, right? But we have basically like this idea of grid following and grid forming inverters. And grid forming being not so common right now. There is still like, there are many researches on that. And at present, this grid following technology is predominant among like these grid connected inverters. So we've been relying more on grid following, and that's why also here we decided to use this grid following. That was the focus of this use case that we are applying this framework just to have this proof of concept, right? In grid following, we have this current source behavior. So the guys will present a little bit more about grid following, grid forming in the next couple of days. But here in this grid following behaviors, it behaves like a current source in a way. This means that they focus on controlling the current output rather than the voltage, making them suitable for strong grid conditions where the grid voltage is stable and can be relied upon for synchronization, right? And usually there are different approaches, there are different approaches there, but usually we have like this idea of plant level controller, and you have this inverter level controller. So the inverter level controller, for example, they include the phase lock loop, is a very characteristic of grid following strategy. Current controller, active power controller, and reactive power controller. When we go to the plant level controller, and then we have some PF, like a power slash like frequency droop controller, and you can have some key view droop controller also. So the way that it will like, like these references will be set depending on some measurements and so on. So that's the main idea of the grid following. So for example, the PLL, which is this part highlighted here. So we have some generic idea of it here also. So it usually measures the phase angle of the three-phase voltage in real time, and then via Parks transformation. So usually here we do this Park transformation because it's easier to get this the angle that we are interested. So we can convert these three-phase variables and then transform it into DC components, which is easily much more easier to handle in this DQ reference frame. So we apply this mathematical technique in the end. That's a different way of representing these quantities. So in the PLL, we usually apply this idea. So there is also the inner current controller. So this is again like a common way of representing it in the simulation block. So here again, we are using PR controllers because here we are also taking advantage of that DQ frame, right, in which the quantities can be represented as DC values. So that's why we can easily apply like a PI controller in this case. So this active power controller and reactive power controller, right? So there again, so there are different ways of doing this. Here I'm showing a specific, a generic way of doing that. For example, explaining how a grid following generic model can be represented of the controller, right? Of grid following controller. And here the PF and droop controller, usually there are some, like curves, some droop that have some, like droop, some angle of this curve, and so on. So in this framework, we used, so we tackled like these specific parameters to calibration. So we grouped them into two based on the sensitivity analysis. We are working more with the reactive power control loop and the active power control loop. And we have 6 PI parameters here that we can tune, that we focus on calibrating in this use case that we proposed at this point. So just to show like what we are, like in this use case, what was the goal? So what was the goal? To calibrate these parameters in this case, right? Of these, so there are more parameters that involve a grid following controller, but we focus mostly on these parameters just to see how that would work in the beginning, right? In terms of the frequency response scan for parameter optimization, so we are proposing this methodology, right? So this frequency scan involves some signal injection, and then you capture the response of the simulation. So you inject the signal, then you do some measurement to capture the response, and then you can calculate the FFT and the transfer function. So the relationship between the injected voltage and the measured current, and then you obtain the bold plot, and then you calculate the cost function. So here we are using this frequency scan as a reference. So we have this reference data for a reference bud plot, and then we calibrate the parameters so that we can get a set of parameters in which we could get a similar bud plot of the reference. That's the idea in the end. But how we do the signal injection, right? So the signal injection for determining the harmonic impedance of the wind turbine generator. And so here again, so we are using this test case with a wind turbine generic model, again as we showed before, right? Can be done by applying a current signal or a voltage signal. So you have these two options. You can inject as a current, you can inject as a voltage. And according to this author, right, that's the author that so the voltage signal was preferred because, right, so they noticed that there was a lower degree of sensitivity to variation of the injected signal, and hence minimizing the need for a trial and error approach. Because when you are injecting the signal, because you are dealing, you need to be aware that you are dealing with a non-linear system, right? So this signal it involves small signal approach. This is a small signal approach. You don't want to, while doing this injection, to really interfere much with that operational point, right? So that's why here they decided also to do this current signal, this voltage signal injection, because they saw that this has a lower degree of sensitivity and minimizing this problem of trial and error. In other words, like to get like a good injection so that you don't leave this constraint of having this small signal idea, right? And the need for a smaller excitation signal and hence create a smaller disturbance on the operating point. And this is important, like smaller disturbances, you get a good result for that response. So that's the approach that we took. So this graph down here shows like a voltage source. So we added this voltage injection here with a small signal. And then we have this transmission line, a transformer, and then there in the IBR, we are measuring there. We are measuring like on the output of the IBR, the current and the voltage. And we are basically, getting the FFT and transfer function of this relationship between current and voltage there, like the impedance scan of this. So again, like these signals can be injected in different ways. Here we decided to do this way, right? So we confine them in octaves. And we summed many like harmonics of that specific voltage. So for that specific region, our harmonic range that we wanted, again, like confined in an octave, because if you put a very big spectrum of harmonics, you can, have some interferences, and you can have some issues by really getting a realistic result out of that. So that's why we decided to confine them. So n is the number of frequency components, ak is the amplitude of the kth frequency component, fk is the kth frequency. And so here, another important aspect of it is that, the phase, the way that we separate the phase. So we did it in a way that in a quadratic phase shift, we did a quadratic phase shift to ensure that the phases of the frequency components are staggered in a non-linear manner, spreading out the energy of the signal and avoiding large spikes. So again, we don't want to, to, violate this constraint of small signals approach, right? So we want to keep it a small signal. And although we are injecting all the signals, we want to keep it small in a way, right? So like spreading the energy across all these different harmonics. Okay, so the way that you calculate it, then, you take the FFT up there, and which is basically like you can be translated by getting like the FFT of the voltage measurement here divided by the current measured, the FFT of the current measured, and so on. So you do it in a way that, and there are many like Python libraries that you can use to calculate this FFT. So and do it, and you can get the boot plot out of that. So you can get like the magnitude and can get the phase. Because from these you get like some complex results that you can translate it into amplitude and phase. So here's some idea of the sensitivity analysis that we performed. And via the sensitivity analysis, you can see that there are, there are some frequency range, like there are some frequencies in which there aren't many, they are not very influenced by the parameters. So this is nice, like to see for a bigger spectrum so that you can see in which frequency range actually is valuable for you to do the calibration. So how we did it? So we changed the parameters of our generic model. And this sensitivity is important to say that this sensitivity is related to the generic model that we are calibrating here, right? And so by looking here, we saw that, okay, so we can concentrate, we can narrow this frequency scan, and we don't need to do like the frequency scan for this whole range of frequency for the whole spectrum. Let's focus on which the parameters they are actually sensitive. So for the specific model, the controller 2 was minimally sensitive to the frequency scan. So we just removed it. It's like the parameters there were not influencing the frequency response. But the frequency scan can be conducted first with a smaller search space, right? So because we removed the controller 2, we could focus on calibrating the parameters for controller 1 and 3. And for the specific model, the parameters of all the 3 controllers showed some sensitivity to time domain experiments, but not for the frequency period domain. So regarding the parameter optimization, use time domain data. So you could do it in different ways. Here, the way that we decided to do it, we were performing some step changes in capturing the response of those step changes. So again, so we are talking about the test cases that were performed, and here we talked about the frequency domain test cases, and here now we enter in these time domain test cases, right? So here we perform some step changes in power, reference power, and the voltage. So we changed also the voltage there to see how that would behave. So we get some dynamic response. We are very interested in the dynamics here, right? So we perform different, trying to gather like more dynamics, you know. You could do it differently. We could reduce it. If you increase the number of tests and you capture more data, of course, if you keep in mind that each particle will do it every time, if you have a pretty long test, it will take more time for your particle swarm optimization to get into a result, right? But that's how the way that we propose here, like that, the way that we did. And so those are the steps that we performed, right? So you can see that the power reference started as 0.5, and then we jumped it to 1, and then we changed the voltage reference, and then we changed the power again. So in some cases, we changed the power holding the voltage. Sometimes we changed the voltage holding the power. Sometimes we changed both. And then we were getting capturing the values of the IQ and ID, so capturing the current, the values of the current, and then we transformed it in IQ and ID to determine then the optimization cost. So we have this example here of how you know, like this blue curve was the reference. So we were changing, like the goal was that this orange curve would feel like or would get closer and closer to the blue curve, right? That's the idea. Yeah. So the curve is a sum. So here we need to be mindful about this normalization, right, during the calculation of the cost function. So we normalize all of them in this per unit system. And so this blue curve is the sum of the ID plus the IQ plus this voltage RMS, the average between the voltage RMS between the three phases. And we sum them. Right? And then that's why we got that curve. And then the orange curve is also the same thing, right? So we changed the parameter. So each particle was changing parameters, like capturing the result of that change, seeing the dynamics, doing the same procedure, and then seeing, like calculating the cost function, seeing how close they were. And based on this, how close they were like, you know, like varying the parameter until they could get a better result. Someone wants to ask something? Yeah, that's awesome. Okay, so that's the idea of this there. So in terms of error metrics and mismatch analysis, right? So that author that I showed you before, guys, that you can access here, this work is very recent in 2024, right? She used PMU phasor data. But you know, like that can be extended. She proposed some of these error metrics and mismatch analysis that involves like error metric using the areas under the curves. Also some error metric using the Euclidean distance. That's something that we are doing, right? Between predicted and actual values. This is easier to use when you have not, if you have measurement data and then it's noisy, you don't like the sampling is not something that is easily determined by you some cases. So you have much more limitations. So in this case, I would recommend to use the area under the curve. But if you have a pretty good, like not that much of noise, you have a pretty good the control over the sampling and so on, the test cases that you can perform. So that's a nice thing about using the simulated data or using HIL simulations or offline simulations in which you have the sandbox, you can perform whatever disturbances, whatever test cases, and get this the capture the responses and use them. So another way of checking the error between the result that you got and the reference is this direction of the first peak value compared to the values, the settling value, the successive positive peak ratio also compare between them, the rate of change of the dynamic response and so on. Yeah, so we have this, the framework was implemented using a generic type 4 wind turbine model. 6 P.A.D. control parameters across active power and reactive power and iron mass voltage control loops were estimated, were calibrated. And then here we show like these original parameters and estimated parameters. So for this use case specifically, for this proof of concept, we use a white box model. So we knew the original parameters beforehand. But as a next step, we plan to use a HIL setup to conduct this. And then we will calibrate a generic model based on the reference data gotten from HIL setup, right? And we will see how we will get. But at this first approach, the way that we did here, we use this as a fully white box in both cases. We knew what to expect. That's what I want to say. So we didn't have a black box IBR control, right? So these estimations, they exhibited on average less than 5% deviation from the original parameters. So this outcome highlights the framework's potential in determining the control parameters using both time and frequency domain data. And although PSO was the chosen method, again, there are different frameworks that could be used and as an alternative optimization method. And the method can be extended to other use cases. Again, we plan to calibrate a grid following and a grid forming generic model. So here we tackled more the grid following one. We could also extend it to the grid forming. And yeah, so, and also using this controller in a HIL setup. So that's the idea. So thank you.